In 1932, the Nobel Prize in Physics, awarded to Werner Heisenberg for his creation of quantum mechanics, marked a profound shift in the fundamental understanding of physics. Heisenberg's introduction of the uncertainty principle was revolutionary, fundamentally challenging the deterministic nature of classical physics. This principle states that it's impossible to simultaneously determine both the exact position and exact momentum of a particle with absolute precision. In essence, the more accurately you know where a particle is, the less you know about its speed and direction, and vice versa. This concept was radical because it contradicted the long-standing Newtonian mechanics, where the state of a physical system could, in theory, be predicted with arbitrary accuracy given initial conditions. In the quantum realm, however, Heisenberg showed that such precision is not just practically impossible, but fundamentally unattainable. This introduced inherent probabilistic elements to the behavior of particles at the quantum level. Heisenberg's theory reshaped the landscape of atomic and subatomic physics. It was essential in understanding the behavior of electrons in atoms, which in turn has been crucial in the development of quantum chemistry and the understanding of chemical bonding. Furthermore, the uncertainty principle has implications for the energy levels of electrons in atoms, explaining why electrons don't simply spiral into the nucleus, as classical physics might predict. The Nobel Prize in Physics for Heisenberg acknowledged a paradigm shift in our understanding of the microscopic world, moving beyond the visible and tangible universe into a realm where traditional rules of physics are supplanted by probabilities and uncertainties. This not only opened new avenues in theoretical physics, but also laid the groundwork for practical advancements in technology, particularly in fields that rely on quantum mechanical principles, such as semiconductor technology and quantum computing. Heisenberg's work thus stands as a cornerstone in the ongoing journey to understand the universe at its most fundamental level.
The Nobel Prize in Physics for 1933 was divided equally between two prominent scientists, Erwin Schrödinger and Paul Dirac, for their groundbreaking contributions to the development of new atomic theory. This was a pivotal moment in the field of physics, marking a significant advancement in our understanding of quantum mechanics. Erwin Schrödinger was recognized for his formulation of wave mechanics, a theory that describes the behavior of particles at the quantum level as waves. His most famous contribution, the Schrödinger equation, is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. This was a major leap forward in theoretical physics, providing a new way to predict the behavior of particles in a quantum system. Paul Dirac, on the other hand, was honored for his contribution to the theory of quantum mechanics, and specifically for the prediction of antimatter. Dirac's work combined quantum mechanics with special relativity, leading to the formulation of the Dirac equation. This equation predicted the existence of particles that were mirror images of electrons, but with opposite charge. This prediction was revolutionary and led to the discovery of the positron, the electron's antiparticle, confirming the existence of antimatter. The work of Schrödinger and Dirac represented a significant shift in the field of physics, moving beyond the limitations of classical mechanics and into a new realm where the strange and counterintuitive aspects of quantum mechanics began to be understood and accepted. Their contributions laid the foundation for much of modern physics, influencing areas like particle physics, quantum field theory, and the study of the fundamental forces of nature. The awarding of the Nobel Prize in Physics in 1933 to these two scientists underscored the importance of their work and its profound impact on our understanding of the universe.
The Nobel Prize in Physics for 1934 was not awarded to anyone. This was not an uncommon occurrence in the early years of the Nobel Prizes. In 1935, the Nobel Prize in Physics, awarded to James Chadwick for discovering the neutron, marked a monumental milestone in atomic physics. This discovery, made in 1932, fundamentally altered the existing atomic model, which until then had only included protons and electrons. The neutron, being electrically neutral, eluded earlier detection, but its discovery was crucial for understanding atomic structure and stability. This breakthrough resolved several perplexing issues in physics, such as how protons in the nucleus overcome their repulsive forces to bind together. Chadwick's discovery had profound implications beyond theoretical physics. It paved the way for the development of nuclear energy and weapons, showing how scientific advancements can have both beneficial and potentially hazardous applications. The neutron's role in nuclear reactions became a cornerstone for both nuclear power generation and the development of nuclear arms, showcasing the impactful and dual nature of scientific research. Additionally, the understanding of neutrons has been instrumental in various fields like chemistry, where it helped explain isotopes, and in medicine, particularly in cancer treatment through neutron therapy. The Nobel Prize for Chadwick in 1935, thus, recognized a discovery that not only expanded the horizons of atomic theory, but also had a lasting impact on technology, energy, and medicine, illustrating the far-reaching consequences of a single scientific breakthrough. The Nobel Prize in Physics in 1936, jointly awarded to Victor Franz Hess and Carl David Anderson, recognized two groundbreaking discoveries that greatly expanded our understanding of both the macroscopic and microscopic universe. Hess's daring and innovative use of balloon flights to detect cosmic rays revealed a high-energy phenomenon originating from outer space. This discovery was not just a mere addition to astrophysics. It fundamentally changed the way scientists viewed the Earth's relationship with the wider universe, opening new research fields in cosmic radiation and its interaction with the Earth's atmosphere. On the other hand, Anderson's discovery of the positron, a particle with the same mass as an electron but with opposite charge, was a triumph for experimental physics. It validated Paul Dirac's theoretical prediction and marked a pivotal moment in the field of quantum mechanics, demonstrating the existence of antimatter and contributing to the development of particle physics. The Nobel Committee's decision to honor both Hess and Anderson highlighted the diverse nature of physics research and its profound ability to reveal the mysteries of the vast cosmos, as well as the intricate workings of subatomic particles. In 1937, the Nobel Prize in Physics, awarded to Clinton Davison and George Paget Thomson, celebrated their independent but concurrent experimental discoveries that provided conclusive evidence of the wave nature of electrons, a cornerstone concept in quantum mechanics. This recognition was not merely for an isolated scientific achievement, but for a pivotal revelation that transformed the understanding of fundamental physics. Their experiments, which demonstrated the diffraction of electrons by crystals, were a remarkable validation of Louis de Broglie's earlier theoretical prediction of wave-particle duality. Davison's collaboration with Lester Germer involved electron beams interacting with a nickel crystal, producing diffraction patterns indicative of wave behavior, a phenomenon previously observed only with light waves. On the other side of the Atlantic, Thomson's experiments, which involved the passage of electrons through thin metal films, yielded similar diffraction patterns, independently confirming the same fundamental principle. These parallel lines of inquiry, culminating in the same profound conclusion, exemplified the collaborative and cumulative nature of scientific discovery. The implications of their work were vast, influencing not only theoretical physics but also spurring advancements in fields like materials science, electron microscopy, and even the conceptual framework for modern technologies. The Nobel Prize in Physics in 1938, awarded to Enrico Fermi, further cemented his status as one of the 20th century's most influential physicists, recognizing his pioneering work that significantly expanded the horizons of nuclear physics. Fermi's innovative approach in bombarding substances with neutrons to produce radioactive elements was not just a testament to his experimental prowess, but also a demonstration of his deep theoretical understanding of nuclear processes. This work proved instrumental in unveiling the complex phenomena of nuclear decay and transmutation, contributing profoundly to the understanding of the atomic nucleus's structure and behavior. Moreover, Fermi's insight into the increased efficacy of slow neutrons in initiating nuclear reactions was a groundbreaking discovery with vast implications. It was this understanding that later became the bedrock of nuclear reactor design, allowing for controlled nuclear chain reactions that could be harnessed for energy production. Beyond its practical applications, this discovery was fundamental in advancing theoretical models of nuclear interactions and particle behavior. The broader impact of Fermi's work extended into various domains, from energy generation to national defense, and raised important questions about the ethical dimensions of nuclear research. The Nobel Prize in Physics in 1939, awarded to Ernest Orlando Lawrence for inventing and developing the cyclotron, marked a significant milestone in the advancement of nuclear physics and had a profound impact on scientific research and medical applications. Lorenz's invention, conceptualized in the 1930s, was revolutionary because it allowed for the acceleration of charged particles to high energies in a compact circular device, using a combination of magnetic fields and electric oscillations. This technology enabled scientists to bombard atomic nuclei with fast-moving particles, leading to the discovery of numerous radioactive isotopes and providing deeper insights into the structure of the atom and the forces that bind it together. The cyclotron's ability to produce particles at high energy levels not previously achievable in laboratory settings opened up new frontiers in particle physics, leading to significant discoveries about the fundamental constituents of matter. It played a crucial role in the exploration of nuclear reactions and the properties of elementary particles, contributing to a more comprehensive understanding of the natural world at its most fundamental level. Moreover, the impact of the cyclotron extended well beyond the confines of theoretical physics. One of its most notable applications was in the field of medicine, particularly in the production of radioactive isotopes for medical imaging and cancer treatment. These isotopes became essential tools in diagnostic radiology and radiation therapy, revolutionizing the approach to detecting and treating various diseases and saving countless lives. Ernest Lorenz's cyclotron also marked the beginning of big science in the field of physics, where large-scale instruments and teams became essential for groundbreaking research. This shift had lasting implications for how scientific research is conducted, leading to the establishment of major research laboratories and collaborations worldwide. During the years 1940 to 1942, the Nobel Prize in Physics was not awarded due to the significant disruptions caused by World War II. This period marked a challenging time for the scientific community, as the outbreak of the war in 1939 greatly impacted research, international collaboration, and communication, which are essential for scientific advancement and recognition. In 1940, the interruption of the Nobel Prize in Physics underscored the global event's impact on the pursuit of knowledge. The following year, 1941, saw a continued hiatus, reflecting the war's redirection of scientific focus towards war-related projects and the limitations on international scientific cooperation.